Okay, over to you, Alejandro.
Okay, perfect. So I'm sharing my screen now. You can see it.
Yep.
Yes.
Okay. So, well, I'm a little nervous, but I think it will be good. Well, the first thing that I wanted to tell you is that I'm not only going to describe Atom. I'm going to describe how TenStreet work until we get to the Atom method. So, and as in all of the beginnings, there is a limitation, a problem which we need to push. In this case, we are talking about the origin of TenStreet, and this begins with the analog to digital converters, which are immersed in some problems. In order to obtain ultra-fast measurement, we need our converter to be even faster. However, right now several problems occur. The first is that we are involved in a trade-off between the sensitivity of our device, I mean the dynamic range, measured in the number of bits, and the conversion speed. As the sampling rate of analog to digital converter increases, it's mean the dynamic range measured with the effective number of bits, its dynamic range reduces. We use the effective number of bits because it gives us more information about the noise. With all this, we have three factors that come into play. Limited gain bandwidth of the transistor, sampling error due to the clock heater, and the thermal noise of the electronic components. We cannot push the thermal noise, but instead we can slow down the signal that improves the transistor speed and the clock heater. By slowing down the signal, TenStreet resolves these issues by suppressing the effect of the aperture heater and the comparator ambiguity. Consider a high-frequency signal being sampled by an analog to digital converter. A small heater will cause a significant error in the sampled amplitude. Whereas if the signal is slowed down by 10 stage prior to the sampling, the effect of the clock heater is considerably reduced. Also, slowing down the signal reflects the comparative speed requirement. So let's explain a little bit of what is TenStreet about. In step one, the information is modulated onto the optical spectrum. For imaging application, this step is a spectral encoding of the data onto the broadband pulse via illumination with a rainbow. Especially dispersed broadband pulse. In step two, the information residing in the spectrum is structured in time by means of a natural or synthetic dispersive element. A group delay dispersive element splits the spectral component in time, causing the information modulated onto the spectrum to be slowed down. This relaxes the speed requirement of the analog to digital converter and enhances the digital performance. Imagine you have a pulse in femtosecond. After the 10 stages, it is several picoseconds. And now we can use the digitizers. In step 3, the optical signal is photodetected, and the digitizers are used like a real-time data converter. And finally, in step 4, consists of digital signal processing and data analytics, such as machine learning or whatever you want to do with the data. Everything I have told you before, we can bring to the file of microscopy. Time states in microscopy is also called serial time encoded amplified microscopy, STEAM. As we see, the first step is to map the object into the spectrum. We do this with the spatial dispersive elements. Once we have mapped the object into the spectrum, we do the pulse time stage, where we map the frequency in time. And finally, we take the pulse to the single pixel photodiode, where we get the spectrum in time. As we see, there are three key points for the resolution of your system. The first of this is the elements that make up the spatial dispersion. Spatial dispersion is used to spatially separate different frequency components of the pulse so that they illuminate different spatial coordinates on the imaging target. For 1D spatial dispersion, a diffraction rate in our pins can be used as a spatial dispersion. Whereas for 2D spatial dispersers, to produce 2D rainbow beam, a pair of virtual image phase array and a diffraction gate can be used as a spatial disperser. These are the most common use in this method. However, in order to map in a space, the diffraction grating and the prints can be obtained for any rates of the spectrum. But this is not always the case for elements for the elements to map in time. The group delay dispersion used in tennessees can be experimental released by using a number of different devices. On the top left, an optical fiber with internal Raman amplification provides high dispersion combined with net gain. The band power is gradually transferred to the signal, avoiding noise and nonlinear regions. This method has some drawbacks. We don't have the fibers in visible bands. On the top right, cheaper fiber Bragg grading is advantageous because you can implement arbitrary group delay profiles. Because many companies provide cheaper fiber Bragg grading with the decelerated group delay. However, the drawback is also the same. You cannot go into 800 nanometer band. On the middle left, a different approach is recirculate the circulating photonic filter using an array waveguide rating in which an arbitrary delay is applied to each channel. So you can manage the dispersion of managing the delay of each fiber. And now we can classify the next method to them that allow to map into the 800 nanometer bands or visible bands. On the bottom left, spectral to angular temporal mapping. This exploits the large modal dispersion of a multimode wave to achieve extremely high chromatic dispersion at 800 nanometers, where dispersive fibers are not available. And finally, the phased method on the middle right and bottom right, where the people use two misaligned pair of mirrors, which creates different paths for every wavelength depending of the angle of incidence. This can be managed to create high dispersion because you have a few freedom parameters. And this is particularly interesting method because it allows to control the dispersion we put on the poles. So I want to put a video that I found in which the author talks about this phased technique to achieve the dispersion, explaining it and where to apply.
We don't hear the sound, Alejandro.
You don't hear the sound. 1 second.
Kevin speaking.
1 second. We can manage this.
You may have to configure things to share your PC sound as well as your microphone. There were captions though on it, so if the captions are the same as the audio, we could just read the captions to avoid.
Yeah, you can read the captions.
Hang around too much. Otherwise, when you share your screen, I think you have to select a box to say you want to share your system audio as well.
Okay. So a few comments about this. We had to consider the importance of this element because they manage the dispersion is crucial, and with the freedom parameters that they had, like the distance between mirrors, the angle of misalignment, they can achieve the dispersion wanted only to changing these parameters. So once we have talked about all these elements, we can evaluate the performance of the system. Now, knowing what is the resolution of each of the three K points. When the resolution is limited by the spatial dispersion, we talk about the spatial dispersion limited. Also, the spread in time element should ideally perform one-to-one frequency time mapping, but this is not always achieved. So we can quantify the change to compare it. And finally, the resolution given by our photodetector. So what we can see in this graph is the following. If the GPD, the grouped list dispersion is larger, the spatial resolution will be limited by the gradient and also the temporal resolution. So now we have some knowledge about the time stage process. Let's move to cytometry. So let me begin to introduce to you your new parameter called data momentum. So in mechanics, all you know that the momentum is equal to the mass times velocity of the objects. Now, instead of using mass and speed, we use information content as well as measurement throughput to be M and U here. The product of these two parameters is always smaller than a constant, and this constant, in fact, is limited by the sensitivity of the sensor. So as you can see in this figure, there is always a trade-off between the sensitivity of the information content versus the throughput. That means whenever you want to get high throughput, you have to sacrifice the information content. And whenever you want to, and you can sacrifice the throughput, and then you can get more information on the content. So here is a summary of some setting products in the market. And as you can see, in the conventional flow cytometry, the throughput is extremely high. It can achieve about 100,000 cells per second. But the information that we can get from the flow cytometry is quite limited, only the side scattering or the fluorescence signal. So in order to enhance the accuracy of cell differentiation or identification, someone introduced imaging flow cytometry by acquiring the images of the cells, the fluorescent images of each individual cell, by incorporating the CMOS or CCD camera. But whenever you incorporate this image sensor into the flow cytometer, you have to sacrifice the speed because the sensitivity is not high enough to achieve the throughput with acquiring the image of the cells. And this can also further reduce the throughput in the high content imaging flow cytometry. So the aim of Aton and their purpose is to push the curve towards this top right corner to achieve high throughput and higher content. But what kind of opportunity that be this brings? The first immediate application is the rare cancer cell detection. As all you know, that in rare cancer cell detection, the appearance of the existence of rare cancer cell is extremely rare, with only about 1 cell in billion of blood cells. And thus, with high contrast and high throughput measurement, the potential application is for the early cancer detection and minimal residual disease detection by individually imaging all the cells in the blood. And the second opportunity is a single cell analysis. In a single cell analysis, we know that there is a cell-to-cell difference in large population of cells. And if we are able to obtain all the cells, all the single cell details, all characteristics of the cell using a high throughput and high content measurement, this can help us to open a new paradigm for cancer resistance biology and immunology. So here are some examples of previously demonstrated 10-stage microscopy, and for example, a red blood cell and also the microfluidic motions. However, all of these are previously demonstrated, and stage microscopy mainly work on bright field images, and thus make it only favorable for stained cell or high contact object measurement. So this is the main image. This image is the experimental setup that Xian et al. His colleagues used to create the atom. As we can see, it is only a stain system with a variant. We are able to identify the portal pulse that is spatially dispersed by the grating that is focused to the flowing cell. This is what we said before, the spectral encoding. And after that, this returns back and goes to the multiplexed step, in which the pair of mirrors they can achieve two opposite phase contrast. Probably this is the main point in these setups. When the pulse is inside the fiber, it goes through the dispersed line with amplification to reach the detector. So the time multiplexes asymmetrical detection pulse is the case of this setup. Normally, in all the cases, the spectrally encoded pulse beam is coupled on axis into the fiber core of the dispersed fiber for the afterward time stage process. In atom, the spectrally encoded pulse is coupled off axis into the fiber core to introduce an oblique detection angle theta between the fiber axis and the beam propagation axis, as the numerical aperture of the fiber core limits the cone of the coupling light symmetric. In effect, it is equivalent to partially blocking the beam detection path, and thus to asymmetrical capture the lights from the sample, giving rise to the 3D appearance, which is proportional to the phase gradient. In the first mirror, we have in the first mirror they put a plus theta angle, and in the multiplexed path, in this way in B, they add a minus theta angle to go into the fiber. So it has two phase constant difference into the fiber. So atom is considered by the authors the second generation of time stage microscopy. So they use another approach to accurate images. Instead of using the bright field image mode of time stage microscopy, they tune the fiber coupling angle a little bit, such they can generate a different phase gradient contrast. And this phase gradient contrast gives the 3D appearance of the cells. And actually, the principle of atom is quite similar to Sliding imaging, which help us to visualize the invisible air or fluid flow. So here is an example of a comparison of atom camera versus CMOS camera, which operates at 23 kilo frames per second. And all you can see here is the microfluidic channel and the cell flowing inside the HeLa cell. And what you can get captured is just blood cell image. And in atom, we can see high contrast and also image each individual cell in the cluster. So instead of capturing the enhanced contrast in contrast for transparent cell imaging, they try to obtain dual contrast in atom. This can be simply achieved by time multiplexing two opposite couplet images. As you can see that for the image A here, they couple it from the top of the optical axis, and for image B, it's below the optical axis. So you can see A and B shows different contrast of the cell, and more importantly, they can simply perform the addition and subtraction of these two images to obtain the pure absorption constant, and also the differential gradient phase constant of the single cell in this single measurement. So you can see the differential gradient phase contrast so similar quality to the differential interface contrast microscopy for this hepatocyte. So now they go to a next step. What if instead of use two angles to couple the top and the bottom, use four angles, the top, the bottom, left, and right. With these four components, they can achieve a total quantitative phase map. This is the quantitative atom, Q atom. As I said before, this steam with a variant. And now the variant is the asymmetric detection module in 4 ways to generate the phase map. Here we have the broadband pulse with the time stage module, and after that it goes to the spectral encoding. We have to emphasize that these steps are interchangeable. We can do the encoding first and then the time stage, or the other way around. The key point here is that they use the knife edge to create the phase contact in all direction, and also they multiplex the signal, adding delays between each pulse. So in Q atom, they modify the system by using, instead of using the fiber Colvin angle, used a knife edge or partially block the collimator beam. And then in A, B, C, and D, they cut a little bit from the top, bottom, left, and right of the collimated beam. And then they have measurement of the cell with multiple oblique detection angle. And from this image, they can obtain the phase gradient of the cell by this simplest math. So after getting this phase gradient, use the complex Fourier integration to obtain the quantity phase map. And this is very rich in information. So after getting this phase image, they obtain some parameters for single cell biophysical analysis, which are all based of the measurement of the phase, optical path length, the height of the cell, and the refractive index. So from this parameter, they can further derive some biophysical parameter of the cell, like the dry mass, or the volume density, phase volume sphericity of the cell. So using these parameters, they try to study the level-free quantification of different cells. In this case, this is an example of hypertrophy of chronodocytes of a bone. So let me conclude with a comparison of the techniques with some conventional approaches, like non-imaging flow cytometry. So in Q-atom, they can achieve a throughput comparable with the non-imaging flow cytometer, but with the imaging capability. So to conclude, Q-atom is a device that potentially opens a new paradigm for multiple parameter measurement in an ultra-fast way, especially for high throughput and high content measurement. So this is all.
Mm.
Thank you.
Thank you.
Yep.
Thanks, Alejandro.
Any questions?
So with your laser now, Alejandro, you have in atom, they achieved what, 26 megahertz
Yeah.
camera frame? With your laser, at what rate do you think you can image cells?
Yeah, they use a laser with a repetition rate of 27 megahertz that is allowed to 6 to 10 meter per second. So in our case, with in the best case with 8 mega, we could do something like maybe 4 meter per second or something like that. Yeah.
However, if the speed of scanning across a microfluidic device is so high, how do you evaluate the minimum number of photons needed? Because you sit on that vein of flow so little time.